So for this lecture, I'm just going through two of our work. One is based on dual polarization Sentinel-1 and what we did for flood mapping. The other is about deforestation mapping. We use Sentinel-2. So these two data sets are freely available, and the codes are available at our GitHub as well. So it should be pretty easy to implement them. So floods, as mentioned by Dr. Armin, are one of the most devastating or destructive natural disasters. So the cause can be from climate change, urbanization, population growth, or other factors. What we need to have is accurate and timely flood maps. They can be used for emergency responses and emergency mitigation. So it's like risk mitigation. As lectured by Dr. Avik, we have synthetic aperture radar SAR from Sentinel-1, which is widely used for different applications. So we saw lots of application out of SAR Sentinel-1, from flood mapping, land use, land cover mapping, object detection. And what we saw from this data, you could easily detect most of the objects of interest on the ground, even as mentioned by Dr. Avik, by a Conan algorithm. So one of the issues most people have is the speckle noise and the complex backscatter patterns of SAR. So for most of the traditional algorithms, they may cause some challenges, or they may increase the complexities. Why SAR data? So there are lots of reasons why we need to use SAR data. One is they are all weather day and night capability. So the weather and the light won't affect them. So you are using microwave signals, not the visible light. So they can penetrate cloud cover, heavy rain, and they are operational over at night. So if you have floods, so you need to consider that that region most probably will be covered by clouds for a long period of time. So the use of SAR, so because of the smoothness of water surface, they appear dark in the SAR data. So they are mostly visible, or you can create even the flood inventory out of those data. And land, urban, and vegetation, they appear bright. So you saw some examples of those places from the presentation of Dr. Prof. Avik. So Sentinel, you have a good revisit time is 6 to 12 days globally. Some places are less, some places they may be more. And then because of the wide swath, 250 kilometer, you can use Sentinel-1 for large scale flood mapping as well. As mentioned, they are independent of the sunlight and atmosphere. So you don't need to consider clouds, haze, or smoke. And they are the best data for disaster mapping, especially floods. And there have been lots of research based on using deep learning for flood mapping using dual polarization VV and VH. The traditional algorithm like thresholding, region growing, and random forest, some of this algorithm was mentioned by Dr. Armin. They require manual feature engineering. Some may struggle in urban and vegetation area recognition due to complexity of backscatter signals. They do not consider spatial information. They heavily rely on pixel level values. So deep learning, so they learn hierarchical spatial spectral features directly from SAR data. So they use spatial information besides the spectral information. Here, the scattering or backscattering. So they can capture local information through CNNs and global contextual information or from vision transformers. So they can handle speckle noise and they can detect complex patterns from the data. Some of these algorithms, they are noise resilient, so they can understand and they can, with excellent accuracy, detect floats out of Sentinel-1. One was developed by us, so we used Sentinel-1 SAR because the SAR data itself, as was explained, it's a microwave signal. So we consider something that was based on signals. So we use or adopted phase-aware token mixing. So it considers the physics of SAR data. So it considers the signals as complex values. You have the real part and the imaginary part. Real part from this phase-aware token mixed is I will show. So it's cosine, and the imaginary is sine. So you can have this t. So you can consider t as SAR feature intensity, VVVH, or whatever features you are deriving from this dual parametric signal. So it can be VV plus VH, VV plus minus VH, or whatever you are considering that. Then you have the theta, which is learnable phase term. So from the method, you can consider it as positional or directional modulation. And then if you concatenate or integrate the cosine and sine of learnable theta, so you have a complex value compatible with SAR data. In most VIT or vision transformers, you have two parts. One is token mixing and one is channel mixing. Token mixing, most of the time, or the idea is to look at special information, and channel mixing, it's mostly focuses on the importance of channels in the extracted features or feature maps. So I explained some. So the phase-aware token mixing uses cosine and sine to model feature as complex numbers, which is compatible with SAR signal. And then the extracted features or the map features, it will be look like a wave itself. So it's better, it can better extract those information from SAR because it imitates the physics of the SAR data. From the wave vision log, so you have it here. Okay, so no, you don't have it, but you can find it in the paper or in the quotes. So you can consider two special mixing, two express for horizontal and vertical information extraction, and one channel mixing or cross-channel mixing. Then these are from vision MLPs or multi-layer perceptrons. Then there is another channel mixing, which is based on standard MLPs. The standard MLPs, they do not consider spatial information. So if there are some ways that they may consider, but not really comparable with VITs. But most of the vision MLPs, they can consider more or less not as good as VITs, but they can extract positional information out of the data, SAR data here in our case. So we use global flood events from United States, Paraguay, India, and Slovakia. So there was dual polarization data, VVVH, with 542 Sentinel SAR chips. We created some features out of VVV and VH. We didn't consider their importance. Sometimes in feature engineering, you may consider which feature may affect the end results most or least, but here we didn't consider that one. We just wanted to test our model against baseline models. So the base models were swing unit, unit 3 plus, attention unit, auto unit, res unit, trans unit, and trans unit plus plus. Trans unit plus plus was the one we developed before. We tested for deforestation mapping based on Sentinel-2. We wanted to test it for flood mapping on Sentinel-1 SAR data as well. So interestingly, our model achieved the best results in terms of our statistical metrics, overall accuracy, precision, recall, F1 score, dice coefficient, and area under cover. So it outperformed all baseline models. So out of our experiments, you will see some results in the next slides. So the model could better distinguish flooded and non-flooded area compared to other base models. So we experience less over and underestimation of floods. And when we check with the feature maps out of the CNN and Vision module, we saw that they were effective in capturing important areas. Some examples. So we have Sentinel-1 polarization data, VV, then we have the flood mask, and this is the results. So the model could capture small and large patterns of floods. So you will see some feature maps. When you are working with deep learning, most people, they may struggle to interpret these models because they are called black box models. So sometimes it's good to see what they see and what they are doing. One way is to look at their feature maps or to have a better understanding of the models, where they focus, so the attention maps. So we have the polarization data VV, then we have flood mask. Then this one is derived from last vision network from the vision block that I explained. So you can see the model is focusing on the flooded area. And then the last one is the last convolutional layer. So you can compare it with the flood mask. So the developed model is a robust, accurate, and efficient flood mapping architecture. It integrates vision, wave-based vision MLPs plus residual learning. So it can learn adaptively flood patterns from dual polarization SAR data. It significantly outperforms other CNN and VRT-based models on Sentinel-1 SAR data. So it shows strong generalization capability on global Sentinel-1 flood events, even considering limited level data. So the model pushed beyond CNNs, which are excellent at capturing local information, and VIT, which are excellent at capturing global information. So we combine them there to create a model which is strong enough to detect floods accurately out of Sentinel-1 SAR data. So the next is deforestation mapping. Sentinel-2 deforestation is a major driver of climate change. So we have Amazon rainforest and Atlantic forest. They are heavily affected by deforestation, and I guess more or less in the news, you see lots of news on forest fires and other anthropogenic effects, even cutting trees, whatever it is. So one way is to monitor this forest and or monitor deforestation at a larger scale with open access satellite data like Sentinel-2. So Sentinel-2, I will talk about them in the next slides, but CNN, as was mentioned in previous slides, they are excellent with local information, but they struggle at capturing long-range dependency. Vision Transformer, they are excellent at capturing global information, but they need large data sets, large ground truth data, and they are significantly heavy for the computational cost. So Sentinel-2, like Sentinel-1, you have a 10 to 20 meter resolution. So you can have detailed patterns of deforestation, even the small scale clearings or tree clearings. So you will have 13 spectral bands visible in infrared, short-wave infrared, which are perfect for vegetation health, canopy structure, and soil monitoring. The near-infrared bands, I guess in most applications, they use normalized difference vegetation index out of infrared and reds. They are excellent for forest monitoring and biomass estimation, and the revisit time is 5 days. So it is excellent if we are tracking rapid forest changes, if there is, for example, a forest fire. Again, they are free and open access. All researchers, all people, they have access to this kind of data. And they are widely used for forest loss detection. And you can extract lots of vegetation indices like normalized difference vegetation index, enhanced vegetation index, and etc. And they are excellent data sources for training advanced deep learning models. So what we did was to create our TransUnit++, which is based on two mechanisms. One is additive attention gates, and another one is headcons. So headcons was developed for extracting multi-scale at local. So it extracts local information at multi-scale, and the additive attention gate, it focuses on most relevant information from encoder to decoder. So it will ignore or bring the weights down on the noisy data or irrelevant data. So in the headcons, we have point-wise and depth-wise comps. As mentioned, they are for multi-scale feature extraction at local. And then units, it's an encoder-decoder structure with skip connection. We have the attention gates, which highlights the relevant spatial regions. It reduces false positives. And VITs, they are excellent at capturing long-range dependencies. So the TransUnit is based on headcons, attention gates, and VITs for deforestation mapping. So it showed excellent capability compared to base models like UNIT, UNIT 3+, attention unit, SUN unit, res units, and the rest. And it shows excellent generalization capability. One thing that we did was to train model using data from Amazon. We didn't show the data of Atlantic to the models, but we tested those trained models based on Atlantic because they have different feature characteristics, and most of these areas from ecology perspective, they are pretty different. So the spectral information is more or less diverse, so it won't be similar. So we use the data from Sentinel Hub. We had 3 data sets. One was 3-band RGB from Amazon, 4 bands RGB plus near-infrared from Amazon, and 4-band RGB plus near-infrared for Atlantic forest. So the developed model reached to 92% accuracy. So it's improved the base model TransUnit from 3 to 6% in accuracy, F1 and precision. For 4-band Amazon, it reached to 97%. So it improved the base TransUnit model by 3 to 7%. For 4-band Atlantic, it reached to 94, almost 94% accuracy, and improved the base model from 4 to 16%. And for spatial transferability, the model showed excellent capability of generalization capability. So we trained it on Amazon, we tested on Atlantic, we reached to overall accuracy of 88% accuracy. So this is one of the examples of ground truth units, attention units, and other models that we tested. The worst was SUNY unit. It was really interesting, but you can see TransUnit plus. So it could capture small scale and large scale patterns. So the model is a powerful and efficient architecture for deforestation using Sentinel-2. It outperforms CNN-based and transformer-based segmentation models. So it showed excellent spatial transferability, which is suitable for large scale and real world forest monitoring. Actually, we tested this model on flood mapping, the previous presentation. So it shows again excellent capability for flood mapping as well. So it was really interesting. Okay, this is from me.